a video about u-substitution, which is probably one of the hardest concepts in Calculus 2 or Calculus 1. I'm not sure which one it comes in, but I'm going to try and present it as straightforward as possible, and it's really complicated. It can get really complicated at times. So u-substitution is a method for kind of analogous to the chain rule, but for integration, and it doesn't always apply in that it doesn't always work. The substitution will always be mathematically correct, but the result you're aiming for to get like a simplified expression that you can integrate and then substitute back in won't always work. So you gotta try and choose your substitution wisely so that you get the result you're looking for. Okay, so here's the whole process for u-substitution. So first what you have to do is set a variable, usually u, equal to some expression in x, but the variable could be anything. It's just x and y and z are usually taken by other things, so we use u. And then once you set u to some expression in x, find du, which is an infinitesimally small change in u, by differentiating. And then once you find du and how it connects to u dx, substitute du for dx according to your relation. So now your original integral has du instead of dx. And 4, substitute u for x instead of x until the integral only has the variable u. And when you substitute u for x, be sure to keep in mind the original expression you set. You can't just start switching u's to x's to u's randomly. You have to keep in mind step 1. And 5, integrate. Hopefully it's going to be easier. If it works, it's going to be something you can integrate easily once you do the substitutions. And 6, once you're done integrating, use the relation between u and x that you originally set to substitute x back for u, so you get your answer in x. And if it's a definite integral, you then evaluate the boundaries. A common mistake is to evaluate the boundaries when the thing is still in u, but the boundaries are in x, like according to x, so that results in the wrong answer many times. So now I'm going to do 2 examples. The first one being evaluate e to the negative 2x dx from 0 to 1. This is a definite integral, and so first we're going to start by 1, set a variable, usually u, equal to some expression in x. So I'm going to try and save space. Okay, u, that's u, equals, so what do we want to set u equal to? We want to set something equal to u so that this whole thing becomes easier, right? You might be able to eyeball it and figure it out right now, but I'm starting with an easier one. So why don't we set u equals to negative 2x, so this just turns into e to the u. U equals negative 2x. Okay, now we have to find du by differentiating. So if we differentiate both sides of this equation right here, this one, get du over dx equals negative 2x du, the derivative with respect to x of that is just negative 2 because it's x to the first, so okay, now we're going to multiply both sides by dx. So on the left hand side we're just left with dx equals negative 2, sorry, we're left with du, sorry, on the left hand side we're left with du equals negative 2 times dx. So now we have a relation between du and dx. Du is equal to negative 2 times dx. And now what we can do is we can substitute du for dx according to our relation here. And there is no negative 2 here, so what we're going to do is we're going to divide by negative 2 in this integral, so that when we substitute du for dx, we are going to already be doing the negative 2 in the denominator, so they cancel out. It's like, an easy way to imagine this is if we rotate this and instead divide by negative 2 here, the same thing, the same exact relation is that dx equals du over negative 2. Du over negative 2. So dx equals du over negative 2. And this is easier because now where we have the dx, we can just substitute du over negative 2. So we get that our integral is the integral from 0 to 1 of e to the... Okay, now I'm just going to go on to step 4 as well. Substitute u for x according to your relation until the only variable is u. So we have negative 2x, and according to what we set in the beginning, u is equal to negative 2x. So it's just e to the u. And according to this relation right here, dx equals du over negative 2. So it's going to be du, and then over negative 2, I'm just going to put it out front. So I'm going to put a negative times negative 1/2. It's the same thing as dividing by negative 2. So now we have our new integral only in du. So now what we can do is we can integrate this easily because EU integrate is just EU plus C. So it's going to be EU plus C, but I'm not going to write plus C because once we apply the boundaries, it's all going to be the same. And so negative 1/2 out front. And we have e to the u as the antiderivative evaluated at 1 and 0. So this is just going to be negative 1/2 times e to the u. Okay, I made almost the most common mistake here. Sorry. Don't do this. Before we apply the boundary conditions, we have to do step 6. Now we have to substitute x for u using this original relation. U equals negative 2x. So this is just e to the negative 2x because u is the same thing as negative 2x. Applied at 1 and 0 is equal to negative 1/2. Okay, that was a really bad mistake. Okay, times e to the negative 2 times 1, so e to the negative 2 minus e to the negative 2 times 0, so e to the 0, which is just 1. I'm just going to write out 1. And that's equal to, now we just distribute negative 1/2, we get negative e to the negative, e to the negative 2 over 2. And then we have plus 1 because the negatives cancel out, plus 1, so plus 1/2. And if you calculate this, you get about 0.43. So that's the answer to the integral, about 0.43. So sorry, I made a mistake in the middle. Sorry, I made a mistake, but that's the answer, about 0.43. To recap, we just substituted u and then rewrote the integral simplified in u, then integrated in u, then substituted back x, and applied the boundary conditions. So now I'm going to erase all this and do our second example. Okay, I think that's good enough. So our second example is going to be find, this is just the antiderivative, not applied boundary conditions, the integral of sine squared of x over cosine to the 4th of x dx. So Seems like they brought out the big guns. This is a little bit more involved, but we don't have to apply the boundary condition, so we get like a clean, exact answer. So how we're going to do this, we have to first set u. The very first step is just set u. And we want to set it to something that there's already, what's in front of the dx is already in the integral, so we can just get rid of that and clump it in with the du. You'll see once we expand it out, kind of. So if we set it to sine of x, then you're going to end up with cosine of x dx, and that's not really going to help us. We're going to cancel out one of them. If we set it to cosine, it's only going to add to the power of sine in the numerator. So what about we set it to u equals tangent of x. We'll see how this works out. So du over dx would be the derivative of tangent of x, and this is just it's just like a fact. I'm not going to actually do this one here. It's secant squared of x. That's the derivative of tangent of x. It's secant squared of x. So times dx, because we're multiplying both sides by dx, and then we bring the dx to this side. So now that we have this, before we plug this back in, we're going to first simplify this a bit. And so this is the same thing as, so then it'll make more sense, sine squared of x over cosine to the fourth of x. So if you imagine it, it's sine squared over cosine squared, and then there's also 2 more cosine to the squared after you're multiplying in the denominator later. So what you can do is you can factor out sine, well, not factor out, but you can get rid of 2 of the cosine squared, 1 over cosine squared, and you're left with sine squared over cosine squared, and that's tangent squared, because sine over cosine is tangent. So tangent squared of x, and we are left with 1 over cosine squared of x. So 1 over cosine squared of x. These are like multiplied. So this is because 2 of the cosines, 1 over cosine squared is left, and this would turn into 4, would turn into a 2 there, and then you're left with sine squared over cosine squared, which is tangent squared. And now what we're going to do is 1 over cosine squared, 1 over cosine is secant, so 1 over cosine squared is secant squared. So that's what pretty much I did tangent of x as u. So that's why. Now we can substitute this in, and now it's going to make so much more sense. So once we substitute back in u equals tangent of x, we get u squared, because u is tangent of x, so tangent squared is u squared. And secant squared x times dx, that's just equal to du from here. So now this is much simpler. U squared du, and now we can just use the antiderivative power rule, and we're left with, we don't have to do any boundaries, so u to the third over 3 plus c. And now, since we don't have to do step 7, step 6 is the last step, we just use the relation between u and x, u equals tangent of x, and substitute it back in to get it in terms of x. So this is tangent to the third, because u is just tangent of x, so u to the third is tangent to the third of x over 3 plus c. That's the answer. So tangent to the third of x over 3 plus c. So using u-substitution, that's the answer. That's it. Thank you for watching, and watch the next video. Bye.